Hi folks, Aaron Harper here again for the second part of the link budget. This portion of it is going to be for the transmit segment, and as you see I've drawn a very overly simplified but for our purposes accurate transmit system on board. First thing is the transmitter, a 25 watt transmitter, which is very similar to the Kenwood ham radio that was on ISS. And this in turn connects via transmission line to an antenna. Now, if you'll remember from the previous video, the antenna had a gain of 6 dB or 6 decibels. The transmitter puts out 44 dBm, which is actually, let's keep our units straight like I told everybody else to do, maybe I should do that too, comes to 14 dBW or decibels per watt. So you start out life with 14 dBW worth of power. Now you'll notice there's a connector there. That's usually the little coax connector that goes from point A to point B. Every connector has a loss. Doesn't matter how good you do it. There is a change in electrical characteristics between the radio through the connector to the transmission line. And even if everything else was perfect, that change would introduce some resistance. So that is usually a connector loss, which in our case, we have a connector loss of 0.5 dB. It's not much, but it does add up, particularly if you have a lot of connectors. This particular one, I have no filtering, no switching, no nothing. It's dead nut simple. And so there's also a minimum of losses. This makes sense for our purposes of just demonstrating it. But bear in mind, in a real system, there would probably be a connector to the amplifier. There would be a connector as well as a transmission line to go to any kind of filter to make sure the frequencies that are put out by the transmitter are actually what's being put out, sort of a safety net. There are losses in the filter itself. If it's going to block one signal, it's going to block all signals to some extent, just hopefully very, very little. Again, connectors coming from there to, let's say, if it's terrestrial, you're going to have lightning arresters. If you, there's going to be other things. And like I said, every connector has got some form of loss. So it all adds up. But in our case, let's keep it at 0.5 dB. That's actually a little high for just 2 connectors. But for example, a real spacecraft with a filter and a little extra protection, maybe a switching system, would have a grand total of 6 connectors for a total of about 0.7 dB. That would be a real world example. So we'll just keep it at 0.5 to make the math easy. You also have the transmission line here. Transmission lines have a certain amount of loss per foot. It's just the nature of what it does. If you can imagine putting water through a pipe, eventually the surface tension of the water interfering with the pipe itself creates friction. And there comes a point where if the pipe is long enough, you're not going to get a whole lot of water out of the other end, no matter how much pressure you put in it. Same thing with the transmission line. If you have a transmission line that is a couple hundred yards long, your transmission line losses are going to be substantial. That's one of the advantages of working with a CubeSat. The transmission line might be as little as 6 to 8 inches long, at which point in time your losses are considerably less. The way to keep your losses to a minimum is to choose the right transmission line. Every transmission line has a different characteristic, and with lower frequencies like VHF at 145 megahertz, you can pretty much get away with murder. In radio, in a pinch, I've seen coat hanger used. And that of course, being broadcast RF, we're talking about basically, or in this case, AM, we're talking about a 1 megahertz signal. When you go into VHF, you got to be a little more careful, but it's very forgiving for all intents and purposes. UHF, the 435 megahertz range, gets a little bit more persnickety, and the transmission lines have losses that you can measure. As you go even higher in frequency, let's say the L band at 900 megahertz, or up into S band and our beloved 802.11 Wi-Fi routers, being at 2.4 gigahertz, you start seeing some major losses, and it's very important to keep the lines short, and it's also important to have the right kind of line. Once you start heading into the microwave region, for example, KU and KA band, let's say KA being at 30 to 40 gigahertz, it starts really acting like light, and it's very critical that you keep things short and that you put things in a waveguide or a very, very low loss cable that is capable of supporting that frequency. And needless to say, that gets more and more expensive as the frequency goes up. Once you start hitting millimeter wave, you can't do a flexible line anymore so much as a rigid waveguide, which is a piece of metal that is specifically engineered to be a resonant cavity. Essentially, it looks like you're plumbing more so than doing radio. The interesting part about waveguides, however, is that if it's properly tuned, if it's perfect, if it's the right size, and most of these things are critically engineered to be exactly the right size. Since it's a tuned cavity, there's functionally no losses. In fact, that transmission line loss, if you want to calculate that for a waveguide, you're almost wasting your time unless it's mismatched in some way. Where things do start adding up is the connectors. Every connector, just like in a regular RF line, the connectors for a waveguide where things are bolted together, the electrical characteristics change. And at that point in time, you start having losses again. And the losses for a connector on a waveguide is much higher than the gold-plated UHF connectors that we would use on UHF. So enough about the waveguides. Bottom line is transmission line losses. Is this, let's say, is, I did the math on it to be a length for VHF, and there's 145 megahertz. I calculated the length at 25 feet. It's probably longer than that, but if it isn't, this system isn't currently working right now on ISS, so it's close enough. At that range, using a decent quality cable, your line loss is 0.05 dB. Negligible, but still present. And like I said, if you have a long transmission line, it starts adding up real fast. That brings us to antenna pointing losses. Spacecraft, generally speaking, stay in a predictable space, but they don't necessarily point themselves in the appropriate direction, and certainly don't point themselves at any particular place on the ground unless they are designed to do so. ISS flies over with the bottom end of the spacecraft pointing at the ground, which is great, but that also means that unless they move the antenna to track a target as it goes over the ground, that there's going to be pointing losses. And so this is something that you figure out the mean of. You cannot calculate this necessarily. There's also another type of loss that happens at the antenna, and that's called a polarization loss. Radio signals come in different polarizations where they are justified, so to speak. You have vertical polarized signals, you have horizontal polarized signals, and you also have circular polarization of two different types. One is a right-hand polarization, which would come at the perspective like so, and one is the left-hand polarization. The interesting part about that is, if there's a mismatch between the linear polarization, in other words, the vertical and the horizontal, you can almost lose your entire signal. Now, like I said, spacecraft are great about staying where they're supposed to be on orbit. They're not so great about pointing at the ground in a predictable form, and especially not when it comes to which way the antenna is pointing. Because if you imagine yourself pointing at, let's say, an aircraft, you can say, okay, the ground is here, but as you move and follow that aircraft's arc, you will be changing the polarization with reference to the aircraft. You might be pointing at the side of the aircraft here vertically, but as it flies past, you're going to be pointing at the rear and changing the polarization altogether. This is why in spacecraft, they generally speaking use circular polarization. Two advantages. First of all, it doesn't care how you orient yourself relative to the spacecraft, as long as part A is pointing at part B and the antenna on the aircraft, on the spacecraft, excuse me, is, for example, right-hand polarization. As long as you're pointing at it with the complement antenna, in other words, a left-hand polarized antenna, you'll receive at the listed gain. But that brings me to the second interesting part about circular polarization. If you do not have the correct polarization, if you, for example, the spacecraft has a right-hand polarization and you have a left-hand polarization, or excuse me, two right-hand polarization antennas, you can still pick up the signal. Unlike a linear polarization option, the polarization of a circular polarized antenna, the decoupling is not absolute if there's 100% mismatch. You lose a substantial part of the signal. Don't misunderstand me. You lose a lot of it, but you do not lose all of it. This means that should you goof and put the wrong polarization on there, and you look at it and say, oh, we can adjust that, and you don't lose the entire signal. This particular one has a antenna pointing loss of 0.5 dB, which is reasonable. It's just a function of it's not pointing at quite the right place, and we're not at the apex of the lobe. If you imagine an apple as a signal, and your signal start is at the stem, and it comes out like so, comes out like a lobe, and comes back in. That is what a radio signal, generally speaking, looks like from the perspective of an antenna. Like an apple, which generally speaking is a little longer than it's wide, at least the apples we have around here, if you have it directly on along the axis of the antenna, you have the greatest amount of signal. If you are not at the apex, at the zenith point on the radiated pattern, you might have somewhat less. It's generally speaking not bad. It depends on the antenna and how much directionality there is. A lot of your high gain antennas, they sacrifice the omnidirectionality of it, but in turn they bring a smaller band of signal, a smaller width of signal, but vastly increase the amount of signal downrange. In this particular case, we're dealing with a 6 dB gain antenna, which is a very, very mild gain. It has a very wide lobe so that it can cover pretty much the entire globe, and has a very low signal roll-off as it goes to the outside, hence the antenna pointing loss. All these bits of information are available if you know the equipment that is used, which is why hams are so excited about sharing what kind of equipment they're using. If you know what equipment they're using, you can look up the tables from the company that manufactured things like the connectors, the cable, the antenna, and so on, and you can get the actual figures that they expect. So now let's take this and put it all together for our transmission system and figure out what our budget is at the end. This is very much like balancing a checkbook. You start off with 14 dBW, or decibels per watt. You need to subtract 0.5, so we are at 13.5. Then you have transmission line losses of 0.05 dB. This brings you down to, from 13.5, brings you down to 13.45. Then you have an antenna pointing loss of 0.5, which means you are now down to, let's see, 12.95. But now you have an antenna gain of 6 dB. So you take your 12.95, you add 6, and you get 18.95 decibels per watt. That's kind of a number that we can't really wrap our brain around. But if you do the conversion, the amount of power that we're actually putting out, now you'll see here transmit EIRP. That's the effective isotropic radiated power. Big words for meaning this is how much power you're radiating at the point. You know, this is what you're after. Doesn't matter what your antenna puts out. This is what matters. It's kind of like saying that, yeah, you might have a car with 1,000 horsepower, but if your transmission doesn't work, the power doesn't hit the rear wheels. This is where the rubber meets the road. So we have a EIRP of 78.5 watts at the antenna. And that is the first step in figuring out the link budget. The second step, the second segment, so to speak, is the propagation segment. This is where it goes through the medium, in our case, the vacuum of space and the atmosphere, and winds up at the third segment, which is the reception segment. Fair warning, what comes next is a lot of math. Stay tuned.